Any value?
Good morning, sir.
Good morning.
Good morning, sir.
I want to ask you something about the paper. So I haven't got it returned.
Yeah. Actually, I'll upload it to Google Drive just after the meeting, and I'll send the link to you.
Okay.
Sir, I wanted to ask from whom do we have to collect the answer papers?
I have left them in the MPI office, so if Sagar or Tripti, whoever is available, you can ask them.
Okay, sir. Thank you, sir.
Okay, so we can start. You can see my screen, right? So we had started to look at congruences last time, and we covered the basic properties such as the fact that you can add, subtract congruences, multiply, and to some extent divide given some conditions. So those are some basic properties of congruences, and those can be combined for more powerful applications. So in fact, what I would like to do today, after we cover some theories, actually look at some problems from RMO and see how we can apply these concepts in some of those problems. Okay. So, but before that, just to recap, I mean, the most basic properties of congruences that we talked about. And in fact, I actually missed to add one property to this, so I'll do that. So, so we know that if we have some numbers A, B, some integers, and whenever we are using any number as a modulus, we can assume that it is always non-zero because a zero cannot be used as a modulus. So if you have some numbers A, B, C, D, then we have things such as if A congruent to B and C congruent to D mod N, then we can add and subtract them or multiply them. And we are talking about division. So if K is congruent to KB mod N, then what is the condition under which we can say that you can cancel K?
GCD of N and K is 1.
K and N is 1.
If GCD of N and K is equal to 1. So this is true, but in fact, this is a special case of a much more general thing what you can see. So I mean, in general, instead of writing it this way, you can say something like this, that let's say if Ka is congruent to Kb mod some, so if N is also multiple of K is what I'm saying. So let us say it's mod Kn. So basically this implies A congruent to B mod N. Okay. Is that fair enough? And here doesn't have, I mean, this condition is not relevant here. this is always true, that if there is a copy of k occurring in the modulus as well as the terms, you can just cancel it, right? Because obviously if kn divides ka minus kb, then n will also divide a minus, right? So you can cancel the copy of k from all the three terms simultaneously. And so in particular, when we are talking about the GCD, so if you have such a term, so if you have ka congruent to kb modulo n, and let's say we know the GCD of k and n is equal to d, so then it is safe to cancel a copy of d from the entire equation, right? So I can do k by d something like this. So I am able to cancel a copy of d from the whole equation. So that was one thing which I wanted to add, which we missed last time. So I mean, this is an operation where we are changing the modulus, which in all the other operations we can keep the modulus constant, but this is the only place where the modulus can change. And so here you'll see the special case that if we say if d is equal to 1, then here that d will completely go away. So basically you will get back the same thing, take on to be model.
Sir,
Oh, no, I made some mistake here.
sir, in the last one, after that, we can also cancel the k by d, because then GCD of k by d and n by d is 1.
Ha, okay, yes, correct. So here k by d and n by d are coprime. So k by d and n by d are coprime. So therefore, what we said earlier, that whenever the number is coprime to the modulus, we can cancel. So therefore, this implies a congruent to b modulo n by d. So in fact, what this means is that if k congruent to kb modulo n, then you can safely cancel a copy of k from the LHS as long as you change the modulus itself by dividing it by the GCD, right? So now you can see how this is a more general statement than what we did here. So this was a special case when GCD was 1, but this is a general case where GCD will not be equal to 1. And I think this is the way I think they are done in Bolton also. So and we are going to require this when we do Chinese remainder theorem. So that's why I have to add that. Okay, and then we also looked at the general congruence equation. So you are trying to solve the general equation ax congruent to b modulo n. So we are trying to find all the solutions for this general equation. And we were again we could convert this into a simple Diophantine equation, because this is nothing but ax plus ny is equal to b for some x and y. So therefore we already know what is the condition of by the Diophantine equation, that the GCD of the two terms on the LHS, the GCD of a and n has to divide b. And in fact, if I call that GCD as d, then we know how many distinct solutions we can expect, right? So this set of equations will have exactly d incongruent solutions modulo n. So which means that within with any range of n numbers, so you can take the range from 0 to n minus 1. So this is the range of n consecutive numbers. Exactly d of these numbers will satisfy this equation. And we also checked some examples now. Okay, so now we want to see how to extend this to more than one equation. So suppose we have two equations, a congruent to x, a1x congruent to b1 mod n1, and a2x congruent to b2 mod n2. Okay, so we want to see how to handle this system in general. And I think last time we already noted that obviously each equation has to have individually one solution. So in other words, for the first equation to have a solution, we require the condition that GCD of a1 and n1 should divide b1, and for the second equation, GCD of a2 and n2 should divide b2. So both of these should be satisfied, but that alone may not be enough, because still it could be that the two individual equations have a solution, but there is no common solution. So now first we want to see what could be the necessary and sufficient condition for a common solution to exist. Okay. So what do you think would happen? As we said last time that let's say the first equation, has an initial solution x1. Let's call it. Okay. So first equation has a solution x1 and second equation has a solution x2. And as we noted, the entire solution set will be an AP starting with x1 and some offset. So it will be x1 plus some k times some constant difference. Okay. K times, let's say t1. So this is the solution set of the first equation, and the second equation will have x2 plus k times t2 for some other. The constant difference may not be identical. Okay. So for all t1. Okay. So these are two arithmetic progressions. So the question is, what is the necessary and sufficient condition for two arithmetic progressions to have a common term? So, I mean, this is an interesting question to think about in general. I mean, not just related to this congruence solving problem, but have you thought about this question that if you have two arithmetic progressions, in what conditions will they have a common term or not? So I'll give you some time to think. Maybe you can try some simple examples and check when they have common term and when they don't have common term. So we can pose this problem also as a Diophantine equation, right? Because what we are saying is that suppose they have a common term. So I have x1 plus k times t1 equal to and maybe the k will not be the same. So maybe x1 plus k1 times t1 equal to x2 plus k2 times t2. So it will be different terms in those two APs. Will not have the same value of k. So what is the condition under which such k1 and k2 will exist? That's what we're asking, right? So do you see how this is nothing but the Diophantine equation which we've always been solving just by some
Yes.
rearrangement? Because I can take x1 and x2 on one side. So this can be written as k1 times t1 minus k2 times t2.
K1 and K2 are variables, right?
K1 and k2 are the variables which we want to find out. So yes, this is basically again a Diophantine equation with two variables, linear Diophantine with two variables. So here, what are the things that you already know? So we know t1, t2, and x2 minus x1. So therefore, k1 and k2 are the variables. And so, what is the condition under which this system has a solution?
GCD of T1 and T2 divides x2 minus x1.
Right. So if GCD of t1 and t2 divides x2 minus x1, then these are the solution. Okay, and by the way, I just mentioned what is T1 and T2 over here. So, I mean, we know what is that constant difference between two solutions. So it is actually N1 upon D1. So the modulus of the first equation, N1, we already noted about that, and D1 is nothing but the GCD. So D1 is the GCD of A1 and N1, and D2 is the GCD of A2 and N2. So the first equation will have D1 incongruent solutions, modulo N1, and the step between any two such solutions will be N1 upon D1, and for the second one, N2 upon D2. Okay. So if this condition is satisfied, so basically all of these three have to be satisfied. First, D1 has to divide B1, D2 has to divide B2. So if these two are valid, then the two equations individually have a solution. And in addition, this condition, what we are saying here. So GCD of T1 comma T2 divides x2 minus x1, then also it has a solution. But of course, there is still a slight complication here that x2 minus x1, those are the initial solutions of those two equations, which we don't know directly. So first, we'll have to solve the two equations, get the value of x2 minus x1, x2 and x1, and then only be able to say whether the GCD of T1 and T2 divides that or not. But so the thing is, Chinese remainder theorem simplifies this problem to some extent by assuming that T1 and T2 are co-prime. So what they do is actually, so if I go back to the original equation, so let's modify the two equations. So the first equation which we started with saying A1 is congruent to B1 modulo N1, and assuming that the first condition is true, that D1, the GCD divides B1. Okay. So now you see we are in a situation where we can cancel out D1 from all the terms, because D1 obviously divides, so because D1 divides A1 and D1 divides N1, because it's the GCD of those two terms, and D1 divides B1 also. So now we can cancel D1 from everything. So I can write, let A1 be equal to D1 into A1 dash. And similarly, you can introduce the dash term for all the three values. Okay, so then cancelling one copy of D1 from everywhere, I can replace this with A1 dash congruent to B1 dash modulo N1 dash. And the purpose of doing this is now if you see what is happening, after we cancel out the GCD, whatever is left is co-prime. So now A1 and N1 are co-prime. Okay. So now A1 dash and N1 dash, they are guaranteed to be co-prime. So we are just simplifying the problem so that it is easier to deal with multiple equations at the same time. Okay. And at this point, I want to introduce the concept of a multiplicative inverse. So I think we all know what is a multiplicative inverse in the normal sense of the term when we talk about rational numbers or real numbers. So for example, we know what is the multiplicative inverse of 2 is half, right? Because 2 into half is equal to 1. This is how it works in real numbers or rational numbers, for example. But something very similar happens in the space of congruences. So as it turns out, if you have two numbers a and n congruent to 1, no, not congruent to 1. If the GCD of a and 1 is a and n is 1, then there exists a multiplicative inverse, a inverse. So a inverse is the notation I'm using. So there exists such an integer such that a into a inverse congruent to 1 modulo n. Okay. So modulo n, you can multiply with this a inverse term and it will cancel out with a. Okay, such a inverse will exist. Can you see why that will be the case?
It essentially means one is congruent to one model.
No. See, this a inverse is not 1 upon a. This is not 1 upon a. So don't think this is an integer, right? This is not a fraction. So, and this is just a notation which I'm into. If it is confusing, you can call it b. Doesn't matter. So there exists a term b such that a into b congruent to 1 mod.
Okay.
So why will such a b exist?
Sir, I did not understand that notation that then there exists a raised to minus
No,
1.
this A is the English thing. So,
Oh, okay, okay, sir.
okay, so why will this be true? Because you can consider the equation ax congruent to 1 mod n, right? This is a linear congruence that we already know how to solve, ax congruent to 1 mod n. And will this have a solution?
Yes, sir.
Right? Because the GCD of a and n, which is simply 1, obviously divides 1, the term which is b. So therefore, this will have a solution. Therefore, such a b will exist. And not only will it exist, it will be unique modulo n. So among the range of any n consecutive numbers, there will be exactly one such term. Okay. And to give an example, suppose let's say take n is equal to 3 and sorry a equal to 3 and n is equal to 10. So what is a inverse modulo n? So in other words, what is the number which you can multiply with 3?
7.
7, right? Because 3 into 7 is congruent to 1 modulo 10. Okay. So why is this inverse useful? Because suppose you have an equation. Let's say you are trying to solve the equation 3x congruent to 5 modulo 10. What can you do now? If you know the
We can
multiplicative inverse,
divide it by 5 to get to 1. So 3 by 5 n is congruent to 1 mod 10 by
no,
5.
I
see,
think we can multiply by 7 and cancel that 3 from there.
yes, correct. But Anushka, just to correct you, what we are doing here, if you want dividing by 5, right, your LHS may not be an integer anymore. So every time you divide, you have to be careful. See, the whole theory of congruences only works for integers, right? Okay. So anytime you are dividing, you have to be careful that firstly, after dividing, will you get an integer or not? That is the first thing. And even if you get an integer, as you saw sometime earlier, that there are some conditions under which you can divide. You cannot always divide, right?
Yeah.
I mean, I can give you example of where you, if you try to divide that way, you get some false equation. So, for example, I mean, 4 is congruent to 6 modulo 2. Now, if you just divide by 2 over here, you get 2 congruent to 3 modulo 2, which is not true, right? So, you have to be careful when you divide or not.
No, so we'll divide the mod 2 also by.
Okay, okay. Then that is fine. But in this case, I think the issue was you are getting 3 by 4 on the left hand side. So we don't know whether that is.
Yeah, that's true.
Yeah, but I think, yeah, now what you said is the right idea. So basically you can multiply with the multiplicative inverse. So if I multiply by 7 on both sides, I'll get 3 into 7, which is 21x, which is x. So x is common to 35, or which is common to 5 more. So you see from this equation, now we have basically eliminated a from the equation. So we are left with x is common to 5 mod 10. So you see we are getting rid of one variable. And we can do this for any equation like ax equal to b. If we know that the a and n are co-prime. So if I am asking you to solve ax equal to b, x common to b modulo n, and where the GCD of a and n is given to be 1. And we know, of course, this is an assumption that we know the multiplicative inverse. But I mean, we can compute the inverse if we require. And so then we can multiply this whole equation with A inverse, and we can get the equation as A inverse AX common to A inverse B modulo n. And now A inverse A will be nothing but 1. So this whole thing becomes X common to A inverse B modulo n. And instead of writing A inverse B each time, let me just call that C. Okay. So let C be equal to A inverse B. Okay. So you see how the original equation had three unknowns, or three constants, a, b, and n. But now with this multiplicative inverse, we have combined two of them. So a inverse b is combined into a single constant. So now it is reduced to just x congruent to c modulo n. Okay. And we can do this for every single equation. If you are solving multiple equations simultaneously, you can do this for every single equation. Okay. So if you, let's say you are starting with two equations, a1, b1, n1, and a2, b2, n2, both of them can be reduced in this way, and you get x congruent to c1 mod n1 and x congruent to c2 mod n. So this is the new system that you are going to deal with.
Sir, but then we are assuming that GCD of A1 and N1 is 1, or
Yes, so I mean that we could assume because we that you remember that dash notation. So this was what we accomplished when we cancel out the GCD from the original equation and you convert everything into the dashes. Then you are guaranteed that the GCD of A1 dash and N1 dash is 1, right?
yes, sir. Yes, sir.
So basically it's a two-step simplification. First, you get rid of the GCD to get this kind of equation where the these two are co-prime. And the second simplification is now you multiply with the inverse that you get rid of the A1 dash also. So I mean, we at the end we'll see an example where you put all of these things together. So now that we have these two equations, x congruent to c1 mod n1 and x congruent to c2 mod n2. Now individually they'll obviously have a solution because now I mean c1 and c2 themselves are the solution. So x equal to c1 and x equal to c2 are respectively the solutions of each of them. And the question of whether they will have a solution together. So for that, what we had referred to earlier, that GCD of T1 comma T2 to divide x2 minus x. So if I interpret that condition here, GCD of T1 comma T2 to divide C2 minus C. And when T1 and T2 are nothing but the number divided by the, so it will be simply N1 and N2 now because the GCD is 1. So in other words, if the GCD of N1 and N2, the GCD of the two moduli divides C2 minus C1, then this system will have a solution. So here we are actually dealing with the most general case, but what Chinese remainder theorem simplifies is that it assumes that this GCD is 1. I wonder why they do that, because ideally I think we should deal with the more general situation. Don't know why they make this simplification. Yeah, I think we can try to formulate the generalization of the Chinese remainder theorem if we drop that assumption. But at least for now, let's try to do it in the simple way. So let's assume that the GCD is 1. Okay. So now the question is, you have one solution for the first equation, one solution for the second equation. How can you find the solution which will satisfy both of them simultaneously? Okay. So let us say we know x1 is a solution of the first equation. This is equation 1, this is equation 2. And let x2 be a solution of the equation 2. So starting from this x1 and x2, how will you find the solution of both of them simultaneously? That is the question. See, if these are small numbers, you can always do trial and error, right? You can just keep trying one after the other and something will work out. But we want a way to find the answer without such trial and error. Yes, Raghav?
Sir, I have an idea, but
Yes.
it does not include using x1 and x2.
Okay, anyhow, you can go ahead.
So now we have the original two equations. We know that x is congruent to C1 mod N1
Yes,
and x is congruent to C2 mod N2.
yes,
So we can rewrite this as x is equal to C1 plus N1 K1
okay,
and x is equal to C2 plus N2 K2.
yes, correct.
Now we multiply the first equation by N2 and then subtract it from the second equation multiplied by N1.
Yes, correct.
So then you get x times N2 minus N1 is equal to C1 N2 minus C2 N1
Okay,
plus N1 N2 K1 K2. N1 N2 minus K1 minus K2.
yes. Okay,
So if you take mod N1 N2, then you will get N2 minus N1 x is equal to C1 N2 minus C2 N1 mod N1 N2. Now you can just solve for x. This is normal coverage.
okay. So what we have done here is we started with two equations with modulus n1 and n2 respectively, and you combine them somehow into a single equation modulo n1 n2. That is what we have achieved here, and then we can solve this. And you see how, let us say we have a third equation. Let's say we are dealing with three congruences. You can repeat this process now. Now you have to combine this equation and this equation. So now you will get a new equation which has modulus n1, n2, and n3, all of them together, right? So this approach can continue to be generalized for more equations. Arnav, do you have any other approach?
Yes, sir. Actually, I know the solution. I read it once
Okay,
using that multiplicative inverse.
okay. Okay, so then just wait for a minute.
Yes,
Let's
sir.
not reveal the idea. Give others a chance to think also. Okay, but does everybody understand what we have done here? So we started with these two equations. We multiplied with n1 and n2, so that we get everything modulo n1 and n2 here. Interesting. Yeah, I think the really clever part in this solution was that, see, here K1 and K2 are the unknowns, right? So we have to make sure that K1 and K2 remain together, which is what we are ensuring here. So that then we can again, when we go back from this to the congruence notation, that K1, K2 go out. So that is what is a really nice way of doing this. Yeah, I think I've seen this for the first time. So very nice. And also, I hope everybody understand how this can continue to be taken forward with third and fourth equation.
Yes.
Maybe just to cross check whether this really works, maybe take some numerical example and verify. So let's say we are dealing with the concrete equation x is equal to 5 mod 7 and x is equal to 3 modulo 8. Okay. So now how you find the common solution of this? And again, I'm taking small numbers for our simplicity, but don't resort to trial and error just because they are small numbers. So then, I mean, if I directly jump to the conclusion, what we are saying is in 2 minus n1, so 8 minus 7 modulo x is congruent to c1 into, so 40 minus 21 modulo 56. So I think x is congruent to 90.
Yes, sir. It is right.
Yeah. So 19 has a remainder of 5 on dividing by 7 and 3 on dividing. Yeah. So this one, and in fact, this time we are very lucky that n2 minus n1 is 1. So therefore, we directly got the answer. In general, maybe this n2 minus n1 will not be equal to 1, but then you already know how to deal with that, right? So yeah, we can do that. Okay, so yeah, that's a very nice way of approaching it. What else can we do? So actually, there is a concept called Lagrange 0-1 blocks. Have you heard of this term before?
Yes, sir.
Yes.
Is it covered in our lectures? I don't
Yes,
know.
I don't know.
Yes.
Okay, then maybe for those who don't know, just to quickly tell what that is about. Basically, you want to find a polynomial. So this is a completely different topic altogether. Okay, so it is about find the polynomial, typically real coefficient, but doesn't matter. P of x, such that let's say we are dealing with a quadratic polynomial. Okay, so find a quadratic polynomial. So to fix a line, we require 2 points. To fix a quadratic polynomial, we require 3 points, such that some values are given. That p of, let's say, 1 is equal to 3, p of 2 is equal to 5, and p of 3 is equal to 6, or something like that. Suppose I gave you these 3 points, and I want to find what is this quadratic polynomial. Now, I mean, because it is quadratic, you can easily like put the polynomial as something ax square plus bx plus c, and then solve for ABC. You get a linear simultaneous system of equations. But what Lagrange 0-1 blocks is the idea. The idea is this way. I would like to write a polynomial as a sum of 3 different terms. Okay, such that, see, I only care if that what happens at these 3 values, p1, p2, p3. I don't care what happens at all the other terms. So I want to ensure that this first term, if I put x equal to 1, this first term will be 1, this other term will be 0, and this term will be 0, and into 3 obviously. So I'll have to this something times 3, something times 5, and something times 6. That is how my expression want to be. So the thing inside the bracket, if I just look at that, then at x, the value of x equal to 1, I want this to be 1, everything has to be 0. At x equal to 2, I want only this to be 1, everything has to be 0. And x equal to 3, I want this to be 1 and everything has to be 0. So if I can construct such objects in this bracket, then my problem is solved. Right? And then, I mean, there is nothing stopping us from extending this for larger and larger polynomials. So how do we construct this fundamental object? So let's look at just the first column, that how can we construct some expression which is 0 at all other places except for 1.
So it basically uses matrices, right?
What did you say?
No, so this concept is similar to matrices.
Matrix, I mean, it looks like a matrix, but what matrices are covering a completely different topic. So better not to confuse that with this one. So I mean, in a way, what we call determinant can be used to solve this problem also, but again, that is a different topic. But just look at this part. So can you think of some expression which is 0 at x equal to 3 and 0 at x equal to 2? So that will be simply something like x minus 2 times x minus 3, right? So this expression will be 0 when you put x equal to 2 or x equal to 3, correct? But when you put x equal to 1, it will be some non-zero term. So if I put x equal to 1 in this, I'll get 1 minus 2 times 1 minus 3, which is not 0. But it is not 1 also. I would like that to be 1. So how can I make sure that this expression is 1 when x equal to 1? So the idea is I simply divide this by this term. So x minus 2 by x minus 3 upon whatever is the value when I put x equal to 1. So do you see this expression now satisfies all the 3 properties? At x equal to 2 and x equal to 3, it is still 0, but at x equal to 1, the numerator and denominator will cancel out and you get 1 nicely. And in the same way, you can construct the other columns also. So in the second column, you will write the expression x minus 1, x minus 3 upon 1 minus 1 or 2 minus 1. So this expression you will see is 0 for x equal to 1 and x equal to 3, and at 2, if you put x equal to 2, exactly the numerator and denominator cancel out. And the same thing here also, right? And combining all of these three terms together, and you see it is exactly quadratic because every term has x squared. So this is how we can compose this polynomial p of x. Okay. I mean, I'm sorry to rush through this because most students already know this, but just a quick recap. But see, the basic concept of this Lagrange 0, 1 block was composing this kind of building blocks, which are 1 at one place and 0 everywhere else. So why is this important for our problem? How can you think of how to apply this Lagrange 0, 1 problem over here? In a way, do you see it is very similar? See, this was solving the problem, find the polynomial such that all of these are true simultaneously. For us, we want to find some value of x such that this is true simultaneously. X congruent to C1 mod N1, C2 mod N2, and C3 mod N3. So can you imagine how to think of this problem like the Lagrange 0, 1 block problem? I mean, suppose x could be composed of three terms similarly. Okay, term 1 plus term 2 plus term 3, such that let's say I want this to satisfy all of three simultaneously. But when we are doing mod n1, so if I take the whole thing modulo n1, okay, which means that I just take the remainders modulo n1, this turns out to be 0 modulo n1, which means that it is divisible by n1, and this also turns out to be 0 modulo n1, and this turns out to be c1 modulo n1. Okay, so this will ensure that x satisfies the first equation. In the same way, somehow magically, if I take everything modulo n2, I want this to be 0, this to be 0, and this to be C2. Can I find some way of creating this expression? So Arnav, did you have the same idea or something different?
Yes, the same idea.
Okay. So let's see how to. In fact, I have not done this in a long time. So let me see. So maybe the first thing I have to do is I have to take C1 outside. So this something times C1, something times C2, and something times C3. So now the requirement is I just want this to be 1 modulo N1, 1 modulo N2, and 1 modulo N3. So let's look at just the first column, okay? I want to find some value over here such that, and let me call, temporarily let me call it some name A1, I don't know. So I want to find some A1 such that A1 is congruent to 1 modulo N1 and it is congruent to 0 modulo N2 and 0 modulo N3. So this is what I can do. See, if A1 is congruent to 0 modulo N2 and N3, which means A1 is divisible by N2 and N3, right? So A1 will look of something of the form some K1 times N2 and N3, right? This is how A1 will look like. Where K1 I have to choose carefully. So I have to find K1. So I have to find K1 such that K1 times N2 times N3 is congruent to 1 modulo N1. Okay, if I find such a K1, then I am done, correct? And now this is a linear congruence, right? This I know how to solve. Because here, so this is where that condition is important. So we started with the assumption that this N1, N2 are co-prime, all of those things. So all of these are co-prime pairwise. Because if these are all co-prime, it guarantees me that So the GCD of n1 and n2, n3 is 1. So therefore, this equation will have a solution. So therefore, such a K1 can be formed. And in fact, in terms of the multiplicative inverse notation that we have, so K1 will be nothing but the n2, n3 inverse modulo. Right? So this is how I can find K1, and therefore I know what is A1. So therefore, I mean, putting everything together, what will my X look like? So X will compose of 3 terms. First term is C1 times this first block, K1, N2, N3. In the same way, C2 will be there, which will have K2, N1, N3. And third term will be C3 times K3, N1, N2. In each case, this K1, K2, K3 are the respective multiplicative inverses. So K1 is the inverse of N2, N3 mod N1. Similarly, K2 will be inverse of N1, N3 mod N2. And K3 will be inverse of N1, N2 mod K3. But do you see that this expression exactly works like a Lagrange 0, 1 block? Because now if you take the whole equation modulo, if you go modulo N1, for example. So if you take the remainder modulo N1, here N1 is occurring, here also N1 is occurring. So this will be 0 and 0. And here this term is congruent to 1 mod N1. So therefore the whole thing is congruent to C1 mod N1. And same way C2 and C3 will also work. Okay, are you following how this whole thing is working and how it is similar to the Lagrange 0, 1 mechanism?
Yes, sir.
Yes, sir.
So note that actually this Lagrange 0, 1 is a problem solving technique. It is nothing special to do with the polynomial problem or the congruence problem. Anytime you want to create such a scenario where it's almost like a on-off switch, right? You see that it's like that term is 1 only in certain condition, everywhere else it is 0. So it's like an on-off switch. So if you have multiple such on-off switches that you can add up together and you can create anything that you want. So let me check if I think this is exactly what Burton also does, right? But let me just confirm it once. N upon Nk. So yeah, so if you see what if you are seeing my screen, I mean they are describing the problem for R congruences in general, but the approach is the same. So here capital Nk is like N2, N3, N1, N3. So the product of all the moduli divided by just one of them. So exactly one term is missing from this product. Okay, so then once you have this Nk, then you solve this congruence Nkx congruent to 1 mod Nk, small nk. So this I think this xk that they are showing are our k, and then finally you have this combination of all of these. So yeah, notation is slightly different, but idea is the same. So I think if you check this solution later on, you will be able to follow that. Yeah. Okay, so this was Chinese remainder theorem. I'll leave it as an exercise for you to follow the exact proof of Burton for all the R congruences. But the ultimate conclusion is that if you have such n1, n2 up to nk, some k equations, then there will be exactly one incongruent solution mod n1, n2, nk. So we could try to do the same thing for your, the example we did earlier, right? So approach which Raghav mentioned, let's see if we get the same answer. Obviously, we have to get the same answer, but so x count to 5 mod 7, x count to 3 mod 8. And let's add one more equation to the, let's say x count to 2 modulo 9. Okay, so you want to solve all of these things simultaneously. Let's add one more. Okay, so there are 4 equations there. X count to 5 mod 7, 3 mod 8, 2 mod 9, 1 mod 11. And you get questions like this, maybe not 4 terms, but in Praveen and Pradnya exams, you must have seen this question. Find the number which divides the remainder of 5 on dividing by 7, 3 on dividing by 8. Okay, so how do we get started with this? So ultimately, I want x to look something like x will be 5 times the first Lagrange 0 block plus 3 times second block plus 2 times third block plus 1 time fourth block, such that modulo 7. So going modulo 7, this all of these blocks should be 0 and this block should be 1, and etc. So modulo 8, this block should be 1, modulo 9, this block should be 1, modulo 11, this block should be 1. So wherever these blocks have to be 0, we just multiply them, right? So here it has to be simply 8 into 9 into 11 into something, that something will figure it out. Here it is going to be here it will be, oh no, sorry. So this is 8 into 9 into 11, but that will just ensure that this term is 0 in these 3 columns. But in this column, I have to ensure that the value turns out to be 1. So I have to divide this by the, you see exactly like Lagrange 0 1 block, because I am going to divide this by the multiplicative inverse of these, right? So the multiplicative inverse of these 3 together, so 8 dash into 9 dash into 11 dash, that will be the denominator. No, 8 raised to minus 1, 9 raised to minus 1, 11 raised to minus 1. And same way in every way.
Sir, won't you need to multiply?
Okay, sorry, yes. So multiplied by the inverse or divided by, then how do I write it?
Maybe you can just directly multiply.
Yeah, okay, fine. Actually, I wanted to write it in the Lagrange 0 1 block notation, something upon something. That's why I was tempted to write it that way. But anyway, that is. So there is not enough space to write it, so I'll just write it below. So this first term, let me call these blocks A1, A2, A3, A4. So then the A1 is 8 into 9 into 11 into the multiplicative inverse of these things, modulo 7. So just to be clear, there's a bracket over here. Okay. So to find this inverse modulo 7, each number itself can be taken modulo 7. You don't have to multiply 8 into 9 into 11 actually. So 8, see, inverse of 8 modulo 7 is the same as inverse of 1 modulo 7. And it turns out to be exactly equal. So inverse of 8 is itself, if you think about it, because 8 8s are 64. So this is in fact going to be 9 can be replaced by 2 and 11 can be replaced by 4. So the inverse of 1 is 1. What is the inverse of 2? 2 4s are 8, right? So and inverse of 4 is 2. So this whole thing turns out to be 8 ultimately. So A1 is nothing but 8 into 9 into 11 into. And in the same way, you can find A2, A3, A4 also. Okay, let's just take a couple of minutes to do this actually. I mean, we know by theory it is going to match, but getting into the habit of doing the calculation is also important. So A2 will be 7 into 9 into 11 into multiplicative inverse of all of those things modulo 8. So again, you can take the inverse term by term. So firstly, let's replace it by 7 can be replaced with -1. 9 can be replaced with 1 and 11 can be replaced with 3. So -1 will be its own inverse because -1 into -1 is 1. 1 is also its own inverse. 3 threes are 9. Interesting. 3 is also its own inverse. So the whole thing is simply -3. So A2 is simply 7 into 9 into 11. Then A3 is 7 at 11. Into inverse modulo 9. Again, 7 can be replaced with -2, -1, -2. So you see how you can be clever at doing the calculations also as quickly as possible. You use the modulus to reduce the absolute value of the term. Negative terms are fine, we can deal with them. So -2 times 4 is -6, right? So 4 is the multiplicative of this. So sorry, 11 is 2, not -2. 2 5s are 10. So this whole product is -20. And finally A4. So A4 is 7 into 8 into 9 into their multiplicative inverse. What is 11? And so I mean this problem is definitely in the territory where you cannot do trial and error. I mean 7 into 8 into 9 into 11 is such a big number that you cannot keep trying value.
In the A3 part, if it's about 9, we can convert -20 to -2.
Your voice was not audible, Anushka. Can you repeat that?
Yeah, I was saying that in A3, if it's mod 9, so we can make -20 a smaller number.
Yes, you can take -20 as
-2.
yes, that is correct. We can replace -20 with -2. That is correct. Yeah. So A4 is what mod 11. So this is my 7 can be replaced with -4, -3 and -2. So let's do it in the positive direction. So
Sir, -6.
7 into -6.
No, sir, no, sir. On A4, answer of A4 is -6.
Okay, answer of A4 is -6.
Multiplicative.
Can you just tell me what are the, I mean, or will just multiply everything?
So -4 and -3 goes to 12, so that gets cancelled, and -2 is -6.
Okay, so -4 into -3 and -3 into -4. So -3 -4 and -2 becomes 6, right? Yeah, okay. Yeah, so this is 12 and 12 becomes 1. Yeah, so 6, right? Why -6? Oh, yeah,
It's -2.
-6, yes, correct. So 1 into -6. Okay, so we have the answer. So A1 is this, A2 is this, A3 is this, A4 is this. So X is simply the first whole thing multiplied by C1. So what were our C1, C2? 5, 3, 2, 1. So if I multiply this by 5, this by 3, this by 2, and this by 1, and add, I should get the solution of my original equation. Anybody wants to do that? I don't want to do that. How can you do this efficiently? So one thing you can do here is quickly notice that, see, ultimately the solution will be modulo the product of all the devices. So modulo 7 into 8 into 9 into 11, right? So any copy of 7, 8, 9, 11 you see, you can cancel out. So first term you see this 8 into 9 into 11 into 8 can be replaced by 8 into 9 into 11 into 1. So I got rid of one term over there. In the same way, so this can be written as 5 times 8 into 9 into 11 plus 3 times. Here also I'm going to do the same thing. So I'm going to replace minus 3 with plus 5. Okay, that's adding 8, which is 5. So here you can replace this with plus 7, but that will make it harder. So let's not do that. Minus.
Even minus 3 and 5 are minus 3 is better than 5.
Minus 3 and 5?
In the second multiplied by 3, minus 3 is better than 5 because the magnitude is less.
Sorry, Anushka, I'm not able to hear you.
No, so I was saying that in the 3 into 8, in replacing minus 3 by 5, minus 3 is better because multiplied by 3 is better than
Okay. Okay, you're saying minus 3 is better. I see. Okay. So, and then
But in A1 also, instead of taking 8 as 8, you can take 1. It would be better.
Yeah, we've taken one only.
that you already done, right? So we have converted 8 into 9 to 11 to 8
Oh,
back
yes,
as yeah. But we
Yes,
cannot simplify it further as far as what I can see. But yes, what we can do is this. See, I can continue to convert this into minus 2 into 8 into 9 into 11, right? I can replace this 5 if subtract 7 from that. But yeah, I mean, at some point, what happens, trying to find such tricks is slower than just multiplying everything and finding the answer. So you have to, at some point, just commit to the calculation and get it done. So ultimately, that will happen. So actually, one way to do all of this very quickly is let's just find 7 into 8 into 9 into 11 first. So let's just find 7 into 8 into 9 into 11 and we'll divide everything by that because we can take this out as common. Then we'll be just left with fractions. Okay, so let's do that.
Then 5544.
5544. Okay. So therefore, my answer is simply so 5544 times. So now I have divided everything by 7, 8 into 9 into 11. Let's not do any of these tricks. Actually, that probably is the best way to look at it. Instead of doing any of these things, I can just directly write my answer is 5544 times. Now it is just 5 upon, see, out of this 8 into 9 into 11 will get cancelled. So I'll be only left with 7. So 5 into 8 upon 7 plus, in the same way, everything will get simplified, right? Do you see that? Or does it turn out to the same thing? I don't know if you're really simplifying anything.
2 into minus 2 by 9.
2 into minus 2.
Minus 6 by 11.
Yeah, no, unfortunately now because when you combine, you have to multiply everything up anyways. So I don't think you'll simplify anything.
while doing that, you can, instead of 5 into 8, you can just use 5 into 1.
We can do 5 into 1 because something that you already know that we can simplify. I mean, the same thing what we done here. Yeah, by the way, I don't usually spend so much time doing calculations, but this is probably one of the times where it seems to be worth. I mean, this skill is going to be useful for you, not maybe so much in pre-RMO, but if you are preparing for JE, really how to optimize your calculation is something you can give some thought to. And hopefully at some point starts to become more automatic, that you think of the right approaches automatically without giving so much forethought. And in fact, even for Olympiad, I mean, particularly in geometry, right, you have a lot of coordinate geometry problems, or other problems which you can approach using coordinate geometry. But if for all of that, you need to be very confident about doing calculations correct. So if that is something you want to do, then spending time to practice and perfect these things is important. So that 554 is going to cancel the denominator anyway. So I don't think we are achieving much by this simplification. So it is still you have to do 5 into 8 into 9 into 11 and combine everything. So I think let's start doing that. Let's just multiply everything and start getting the answers.
Three nine six zero.
At least we are 99 to help us to some extent. Thank you. I think I multiply this whole thing by 3 also.
Yes, sir. So that above one is 6237 minus 6237.
Okay. This it is 3 times this number, right? So this was
Yes,
2079. So 9 is yeah, 927. So only one more time. So then 7, 8, 9, 6. This is 55 square minus 3024. So the answer is 3960 plus 2264 minus 6237 minus 60. Actually, multiplying everything was faster than trying to find some clever simplifications. That happens often. 6224 minus 9. Minus. So I hope after so much effort our answer is correct. So minus 3037, or I can add a copy of 5544 to it. Two 507. So claim is that 2507.
Sir, that it should be 2464, not 2264.
This is 2464, 22.
Yes, sir.
56 into 44. Yes, correct. 446. Then this answer also will be 64. So 2707. What are the equations that we have? 507. Okay, so at least one mod 11 seems to be correct because 2706, 11 divided 2706. So this is true. Is it 2 mod 9? No, it is not 2 mod 9. So we have some mistakes on there. This is 3 mod 8.
Yes, sir.
And this is 5 mod 7. 9. Yes, this also. All of these are true. This maybe we have some mistake in this term. 2 mod 9. So interesting thing. I didn't expect this. See, 3 of them are true, the 4, this one is not true. So you see, we can backtrack and figure out which term we made the mistake in because we used the Lagrange 0-1 approach. So the 0-1 block of the mod 9 was the one where we made some mistake. But anyway, I think we already spent too much time on calculation, so I don't want to continue this. But I mean, in principle, it can be done. As I said, the modulus 5544 is so big that you cannot keep doing trial and error. So some systematic approach is used.
Sir, I think you took plus 2464 instead of minus 2464.
No, I should have taken minus. Oh, there was a minus sign here. Yes, correct. Forgot. Yes. So then this everything will become minus. So ultimately, my answer will reduce by twice 2464. So I should subtract. So if I subtract 2464 into 2, so what was my answer? 2707 minus 2 times 2464. That should hopefully give me this. If I just compute modulo 9, I don't need to check everything else, just modulo 9 is sufficient. So modulo 9, what is the remainder of this? 14. 7 modulo 9 minus 2 times. This is 12. 7. So this is minus 7, right? So it is common to 2 modulo. So yes, everything is worked out. Okay, so I mean, yeah, this was a lot of calculation, but I hope everybody followed what was the basic approach, that how we compose the Lagrange given blocks and then finally multiplied it with the correct coefficient and then added them together. And realistically, even this kind of calculation will not be expected in any exam, but so we are at the upper limit of what we need to do. Okay, so I think just want to give a review of where we are right now in terms of what is the number theory that we have covered so far and what we need to do ahead. Because the thing is, I would say almost 80% of what your RMO level problems will encounter can be done with what you studied so far. So we know induction at this point, we know divisibility, GCD, LCM, those kind of things, linear combinations, Diophantine equation, linear Diophantine. And now we need to do congruences and the Chinese remainder theorem. By the way, this what I told you is an example of Chinese remainder theorem. But as I said, I encourage you to go through Burton and read the more complete handling of that. So all of this, as I said, is sufficient to do majority of the problems at RMO, and we'll see some examples of that now. What we'll do next in the coming few weeks is, and we have now done prime numbers formally. We all know some basic properties about prime numbers, and those will help you to solve problems, but better to cover it formally. So this is yet to come. So prime numbers, and then some theorems using congruences. So there are standard theorems such as Fermat's theorem, Wilson's theorem, and Euler's theorem. And there are some functions like what we call number theoretic functions, right? Number theoretic functions. Again, some of this you already know. So, for example, the phi of n, which is the number of co-prime numbers and things like that. And finally, formally, we need to cover all the Pythagorean triplets. So, Pythagorean triplets. Okay, so roughly speaking, all of this together forms the first 7 chapters of Burton. So after that, chapter 8 onwards are more advanced theory things that you can read for your own interest, because if you start to like number theory, that is a good starting point for a lot more complex ideas. But as far as problem solving tools are concerned, I am saying that these 4 topics are the most important problem solving tools, and these are required sometimes, not all the time. So depending on maybe 1 out of every 5 problems may actually require you to deal with these tools. Along with these, there are some other techniques, such as, for example, a very common idea is called estimation or bounding. The idea is simple, that you try to put some limits on what can be the smallest or largest solution, and then that gives you a scope of how much trial and error you need to do. Okay, so kind of to limit how much trial and error is required, you can use some kind of estimation technique. The induction, I think we already talked about. Finite descent is another technique which is closely related to this, which can be useful. Okay, and a few other things which we will discover as and how we do some problems. Okay, so so now let's jump to some problems and how we can solve these, apply these things for various Olympiad problems. Okay, but any doubts in the theory covered so far? As I said that I tried to follow to a good extent what Burton is doing, but somewhere I might have deviated and tried my own approaches. So anything is unclear or you want to make sure that everything is perfectly covered, you can always refer to Burton for that. And I think Burton themselves have a lot of solved problems at the end of their textbook, so you can refer to that. So let me head to the problems. Sorry. Yeah, sorry. Actually, the thing is, I have a PDF which has all the RMO papers from. So Maharashtra used to conduct its own RMO exam, and we also have a central RMO paper. So every year we basically have two RMO papers, one from our region and one from the center. So there is a PDF which has all the papers, but it's not opening for me. So, but I'll try to open it. And in fact, I'll post it on Google Drive so everybody has access to that. But for now, let me just copy the questions from that, and then we can try to attempt it directly.
Sir, have they diluted the RMO stage permanently or only for this year?
We don't know actually. So depending on what is the COVID situation and also what is the logistics available, they may decide something different next year. So right now I have no idea. So question, paper. So I'm just giving the question number and the paper number here. So if you want, you can refer it back. So this is a central RMO, so it was the national. So I'll give you a couple of more questions so you can try them. There does not exist.
Sir, are you sharing the screen or?
Oh, sorry, if you're not able to see it. Oh, sorry. Okay, so the first question was from CRMO 2005. If x and y are integers such that 17 divides these two polynomials, x square minus 2xy plus y square minus 5x plus 7y, and x square minus 3xy plus 2y square plus x minus y, then prove that 17 divides the polynomial this one. So this was from CRMO 2005 question. And the second question I am writing just now is from 2009. Solution. I'll give you one more problem. I'll explain what is notation means from the floor function. So this is the floor function, which is basically a round down function. Round down. Okay, so you basically any integer remains the same. Any non-integer is rounded to the nearest integer below that. So the floor function of pi is 3, for example. And negative values also are rounded down. Okay, so I'll give you some time to try, and you don't have to finish all of these today. Important with contest problems is that you take as much time as you want. So actually what I have in PDF is all topics combined. It would be nice if somebody can compile the subject wise separate PDF, one for number theory, one for geometry, but we don't have that.
Sir, in third question, won't that n by root n always be root n only, like floor of root n?
Oh, sorry. It is one more down. So it is floor of floor. So n divided by the floor of square root n, and you take the floor of the whole thing once more. So I'm just give you an example. So 8, 10 will be 10 upon this is floor of, so root 10 is 3 point something. So the answer is so I hope you are trying the problems in the order 1, 2, 3, because I think they are going from easy to harder in that way.
Sorry, sir, can you repeat?
I hope you are trying the problems 1, then 2, then 3. I mean, they are going from easy, medium, hard that way.
Okay, sir.
Okay, so don't want to reveal the answer so that you have more time to think, but just to indicate what can go wrong in question one, depends on how you are trying it. See, one may be tempted to add or subtract the equation so that the x square will cancel, or you multiply with something and then you add or subtract so that some of the square terms get cancelled, right? But the thing you have to remember is anytime you add equations like that, you are always losing information. In the sense that if 1 is 2 and 2 is 2, but if I add them to get a third equation, that is not an if and only process. So first try to extract as much information as possible from the individual equation before you try to combine them. So if there is x and y which satisfies the first equation, then what can you say? And if there is x and y which satisfies the second equation, what can you say? And then we have to look at the intersection of both sets.
We could like try factorizing it.
Yes, that is one idea.
Then I factorize the first polynomial.
Wait, so let's give everybody a chance to try. So if you have a solution, just write it down. I'll come to you.
Oh no, so I don't have a perfect solution.
Okay. Yeah, but certainly you can try to factorize it. If you see a chance to factorize, you should try it definitely.
Excuse me, sir.
Yes.
Actually, I have a class after this at 11:30. It is offline, so I may have to leave in 2-3 minutes. I'll watch the recording on YouTube for the last few minutes.
Yeah, sure, no problem.
Bye, sir. Thank you, sir.
Yeah, bye. Okay, anybody has solved question one?
I've got half part of it. I'm trying the second part.
Okay.
They've almost solved it. I'm just doing the calculation.
Okay, yeah, I'll give you some more time. Oh, now I realize why that file was not opening. So I don't have the PDF as the LaTeX file. I need to compile it. Okay, so we'll look at the first problem, P2.
Yes,
Hello,
sir,
so I'll
I
send
solved
you-
the first one.
Oh. So I'll send the PDF for you also, but as I said, it has all questions mixed, so you have to take some time to figure out which are the number theory questions. Okay, so how do we get started with this question? Yes, Arnav?
Sir, I think we can factorize the second given polynomial.
Yes, correct. So I think x minus y is a common factor which emerges out of the second part.
Yes, sir.
So, and the fact that 17 is a prime number also helps us, although we have not covered that formally, but we know some properties. So I think this turns out to be x minus y times x minus 2y plus 1, correct? So 17 divides this. So 17 has to divide either one of the two, right? So I think we can make cases. So case 1, that 17 divides x minus y, and case 2, that 17 divides x minus 2y plus 1. And so if consider the first case where 17 divides x minus y, and also before that, can you simplify the first expression in some way? Can you think of some way to simplify it? I don't know if you require it for your solution, but
Sir, actually, I didn't try that.
Okay. Then for, I mean, in the general, one thing which you can always think about trying, even if you don't require in this solution, is that, see, clearly x minus y is important in the second term, right? So you have to somehow relate x minus y to the first bracket as well. That is what you want to try. So clearly out of this part is x minus y bracket square. But this remaining minus 5x plus 7y seems a bit odd. But what you can do is, it is very close to, I mean, the minus 5 and plus 7 are very close. So we can make some adjustment. And you see, I can write this as x minus y square minus 6 times x minus y. And so here it will be minus 6x plus 6y. So what else I need to do to make it equal? Just need to add x and y. Okay, so you see, I can write it this way. So it is it has x minus y primarily, but also one x plus y term is coming. Okay. So it might just simplify our calculation, because now you see what happened in case 1. So case 1, when 17 divides x minus y, so 17 is already dividing all of this. So I can directly say therefore 17 divides x plus y also, right? And if 17 divides x minus y and x plus y, I don't think it's hard to see that it will mean that 17 has to divide x as well as y. And then naturally that will mean like whatever we wanted to show, that is all x and y terms only linearly combined. So that will obviously be right. So and in the second case, what do we do now?
So similarly, we get that x is congruent to 2y minus 1 mod 17, and then just we input 2y minus 1 as x in the first one, and get
Yes.
get y square minus 5y plus 6. And if we input that same 2y minus 1 in the to prove that, we get it 2 times y square minus 5y plus 6.
Yeah. Okay. So basically, what this allows us to do, and this is where you can start to see how congruences can be useful, because I mean, in a normal equation, if you got something like x equal to 2y minus 1, you can substitute and eliminate that variable. We are going to do the same thing here in congruence notation. So wherever you see x, you can replace it with 2y minus 1, and as long as we are dealing with modulo 17, everything will work out. Okay, so when you do that, so this whole expression, so if I call this expression L1, so L1 will nothing but will be congruent to. So important now it is congruence, not equality. So instead of x minus y square, I can write 2y minus 1. Okay. So it will be basically y minus 1 square minus 6 times y minus 1 plus 3y minus 1 modulo 17. Okay. And as what Arnav was saying, if we expand and simplify this simply turns out to be y square minus 5x plus 6. So L1 is congruent
Y
and this
square
whole thing
minus
is
5y
congruent to
plus
0.
6.
Sorry.
Y square minus 5y plus 6.
Yeah. Correct. So y square minus 5 plus 6. And because we are given that 17 divide this, which means that this is common to 0 mod 17. Okay. So basically, or putting it back into divisible terms, 17 divides minus y minus 2 times y minus 2. So therefore either again here we'll get two subcases, right? So subcase 1, 17 divides y minus 2, and subcase 2, 17 divides y minus 2. Okay.
So actually, we don't require that.
Achha, we don't. Then what do we do?
Sir, if we just input x is equal to 2y, congruent to 2y in the to prove that, we get it as 2 times y square minus 5y plus 6.
Oh, interesting. So what we have to prove is that 17 divides what was that expression? Xy plus
xy minus 12x plus 5y, 15y.
Okay, so here you will substitute x equal to 2y plus 1 or congruent to 2y plus 1. Okay.
Yes. Yes, sir, and we get 2 times y square minus 5y plus 6.
Oh, interesting. Okay, so then if this is congruent to 0, then obviously this is also congruent to 0. Okay, that's interesting. The approach I was going for was, and maybe again, as I said, maybe you don't need to do that, but just as a problem solving technique which can be useful somewhere else. So, I mean, first thing which I did was, again, this minus 12 and 15 were too big. We can substitute them with smaller moduli. So, minus 12 can be replaced by plus 5. So, it's enough to show that xy plus 5x minus 2y is common to 0 mod 7. And here, when you see this kind of pattern where there are 3 terms available, you can always try to complete the factorization, right? By adding a 4th term. So, what is the 4th term you need to add over here? Minus 10. Right? So, if I subtract 10 from both sides, you see now the LHS is nothing but x minus 2 times y plus 5, right? And minus 10 is plus 7. So see, the original equation was so ugly to look at. What to prove that? To prove that this versus to prove that this looks much more simplified. Ultimately, I don't think it really matters. I mean, you can do it either way. You can take the cases and substitute values and check it out. But I mean, just note how simplification can be useful to in some problems. So just to complete the two cases. So, so case 1 is 17 divided by minus 2 and case 2 is 17 divided by minus 3. So in both cases, basically, now if I write everything modulus 17, so y is common to 2 and what x was 2y minus 1. Right? So x is 3. And the second case, y is common to 3 and x is common to 5. So you can substitute both of these pairs into this equation and check that they satisfy. Okay, everybody follows this approach.
Yes, sir.
Yeah. But yeah, in fact, what Aruna did was also useful. So, I mean, basically, it's always useful to think of it from both directions, that you simplify what you want to prove as well as you simplify the given information. So, when you make both the ends meet together, typically the problem should be solved. Yeah, okay. So, I mean, we are almost out of time, but so I hope you have noted down the question numbers here. So, this is 2005 question 2. 2009 question 2 and 2010 question 6. So I'll send you the PDF so you can look at these questions offline. And also, I mean, in general, now I'll encourage you to, as I said, you have studied a significant number of theorems or so to say. So you can start looking at the problems in the RMO papers. And wherever possible, I think you have to take a call. If you come across a problem which you think might be tricky to write down, I think you should write it down. If some problem is there where you are confident that you can write it down properly, you can go ahead. But I mean, you have to trust your judgment. You should not be in a situation where you think you can write it properly, but when you actually write it, you make a lot of mistakes. So maybe err on the side of caution, at least to begin with. Okay, yeah, we don't have time for further. And
Sir, in the last in this question 17 divides, instead of 17, if we take any prime, it will work, right? Because we never use 17, I think.
Yeah, in my solution, I did use 17 at one point, but more is not problem. That is true, actually.
Because we just required that 17 is a prime to get that p divides x minus y or x minus 2y plus 1, and then we just substituted x is equal to that something.
Yeah, I guess we only need it to be an odd prime because in your solution you are getting 2 times y square minus 5 and 5 plus 6, right? So as long as it's an odd prime, it should work.
Yes, sir.
Yeah, I think that is.
So 2 won't work, but others will.
2 won't work, but any other prime should work. Interesting. Yeah, so I mean it's a interesting point. So also useful to, after you solve every problem, check what is the information you used and what you did not use. And turns out if you didn't use something, then that was redundant. Okay, yeah, I don't think we have time for a puzzle today. But anyway, so we'll continue with some problem practice next time also. If possible, I'll send a list of problems which you can try from these RMO papers, and you can take some time to try them. Okay, that's all. Thank you.
So you are sharing the PDF of problem on Drive or group?
It is on my Google Drive, so I'll send a link of that on our.
Okay, sir. Sure. Yes.
Okay, bye.
Thank you, sir.
Thank you, sir.